Okay, good morning, everyone. Let's dive back in. It's been a while since we've met. Last time was town meeting day. There was no quiz, no lecture. And next week, also no classes. If you're going somewhere nice next week, don't tell me, because I'm not. So enjoy, and then we will all be back together again on Tuesday, the 18th. You will be continuing to work on your assignments if you are going somewhere nice. Try and finish it up before you go or after you come back, but just make sure that you're submitting things on time as usual. Any questions about the assignments? Any questions about the A's? Any questions about the D's? Going once, going twice. Okay, back to lecture. So we are going to finish off lecture 10 in a moment. Where are we here? We're going to finish off lecture 10 in a moment, which will finish up our admittedly brief history of evolutionary robotics. And then starting today, we will dive into a series of subsequent modules of the course dedicated to different aspects of embodied cognition, starting today with locomotion. But before we talk about locomotion, let's finish our discussion about ACP, or active categorical perception. Again, since we haven't seen each other for a little while, just to remind you what we're doing, we're looking at a robot that is going to be evolved to solve ACP, where as part of solving ACP, the robot is really solving two subproblems. Reducing within category differences, manipulating objects that may feel similar but that belong to the same class. So perform an action that reduces those differences that exist across objects that belong to the same category. And then at the same time, as you are acting and manipulating these objects, magnify between or inter-category differences. There may be subtle differences between the objects you're being tasked with categorizing. In the case of the robot, it needs to be able to distinguish spheres from ellipsoids. The investigators chose the major and minor axes of these ellipsoids so that they look and they probably feel quite a bit like a sphere. That's the challenge in front of the robot. Just to remind you, it's an anthropomorphic robot. It's got quite a few mechanical degrees of freedom, lots of joints, lots of motors, lots of sensors. We looked at the CTRNN last time, made up of 47 neurons, arranged into sensor neurons, hidden neurons, and motor neurons. And we ended last time by talking about these two categorization neurons, 47 and 48. And we drew a visual or geometric representation of what these two neurons are doing and how their values are going to represent the robot's voice, how it's going to try and tell us or tell the evolutionary algorithm how or whether it's performing active categorical perception. So we're going to plot the value of neuron 47 on the horizontal axis, the value of neuron 48 on the vertical axis here, and we're going to look at the values of neuron 47 during the last 5% of the time steps that a CTRNN is being evaluated in a simulation. As we do, we've got value 47 and 48 at 0.95 times uppercase T, so 95% of the way through the simulation. Then the value of 47 and 48, one time step later, one time step later, one time step later, one time step later. And across the course of one simulation, while the robot is in contact with either the sphere or the ellipsoid, we get this little trajectory. And the math here indicates that we're going to draw a little bounding box around this trajectory, and this bounding box represents the robot's a rectangle associated with sub S here, sub S for sphere, and I'll just put 0 here. This is the robot's experience when in the presence of the sphere for the first time. Computer scientists always count from 0. Remember that the robot doesn't necessarily know it's in the presence of a sphere or ellipsoid. This is just what it feels, what these neurons do. Then we place an ellipsoid underneath the palm and evaluate the same CTRNN again, and we get a different trajectory, and this becomes the bounding rectangle around the ellipsoid, D for ellipsoid, 0 for the first ellipsoid that this CTRNN has come into contact with, and so on. I'm not going to draw all 8 evaluations of the CTRNN with the sphere. Let's just do one more. Let's assume that when the robot, or when this CTRNN is in the presence of the sphere for the second time, it produces this trajectory, and when in the presence of the second ellipsoid, it creates this bounding rectangle. Okay. Then they go and draw 2 more bounding rectangles, one big one, CS, around all the bounding rectangles associated with the sphere. So this becomes CS, YCS, C for category or classification of sphere. These are the sensations the robot collected while in the presence of the sphere, and one big bounding box here. Here are all the experiences the robot had in the presence of the ellipsoid. So far, so good? So we've talked about the problem that the robot is trying to solve. We've talked about the robot's body. We've talked about the robot's brain. And we've now talked quite a bit about these 2 neurons within the brain. Now let's pull back and talk about the evolutionary algorithm. As always, the investigators create an evolutionary algorithm that starts with a random population of CTRNNs. They're going to take each CTRNN and download it into the robot 16 times, 8 times in the presence of a sphere, 8 times in the presence of the ellipsoid. And then for that first random CTRNN, they're going to compute the fitness function. What's the fitness function? We want to create a function that assigns a scalar. It assigns a floating point number to that CTRNN, where that number represents how well or how poorly the robot is performing active categorical perception. They're going to compute this fitness function using these 2 bounding boxes, CS and CD. What relationship would you like to see between these 2 bounding boxes that would represent good ACP?
We want to maximize the distance between them.
We want to maximize the distance between them or minimize the overlap between them. Why? Why is that good ACP?
Because that means it's magnifying the differences between the 2 categories.
Absolutely, right? So by pushing these apart, it's magnifying the felt differences. Its felt experiences become more and more different when in the presence of spheres and when in the presence of ellipsoids. Let's assume a random CTRNN actually does a very poor job at enabling the robot to do ACP. It produces this for CS and it produces this for CD. Yes, this doesn't magnify intercategory differences, but why is that kind of a bad thing? Why is that going to make it difficult for the robot to distinguish between spheres and ellipsoids? What happens if we place an object underneath the robot's palm when armed with this CTRNN and it produces this trajectory? This is what the robot feels or experiences when in contact with this object. What is the robot telling us? What is the CTRNN telling us? What is this object? Okay, I see some shrugs. That's good. That's kind of what the robot is doing. What is it actually saying, aside from just shrugging?
It's neither a sphere nor an ellipse.
From its perspective, it says, I don't know what this object is, but whatever it is, it's neither an ellipsoid or a sphere. Yeah? Okay. You can probably guess what I'm going to do next. What if we place an object and it feels this? What does the robot tell us in this case? It's both, or it could be either, right? It's either both. It's kind of ellipsoidical and spherical, or yeah, it's both. Or I don't know, right? This is problematic. When these 2 bounding boxes are non-overlapping, this case never exists from the robot's perspective. It's either a sphere, an ellipsoid, or it's neither. Yeah? Okay. Here's the actual fitness function they use. So FF, or fitness function, equals F1 plus F2. So we're going to start to see this in the latter half of the course here. We're going to start to see some more complicated fitness functions because there's kind of a lot of things the robot needs to do to actually solve active categorical perception. It does need to minimize the intersection or the overlap between CS and CD, but there's some other things it also needs to do. So let's have a look at what they did here. They've got F1 plus F2. So the evolutionary algorithm is actually trying to maximize F1 and F2. There's two things that the evolutionary algorithm is trying to find CTRNNs to do. What is F1? Well, let's dive inside and start to figure out what some of these variables are. Let's start with D sub E here. D sub E is the Euclidean distance between the object sitting on the table and the center of the palm of the robot at the end of the trial E. So we're going to iterate, we're going to sum up over a bunch of evaluations of the CTRNN. Uppercase E is 16. We're evaluating each CTRNN 16 times. Yeah? Okay, so let's work our way from the inside out. What is this ratio? D sub E, distance of the robot's palm from the object at the end of trial or at the end of evaluation E, and D sub max is the maximum possible distance the palm can be from the object. If the evolutionary algorithm runs and starts to evolve CTRNNs that achieve higher and higher values of F1, what is the robot doing? What do those CTRNNs cause the robot to do?
Put its hand on the object.
So it's 1 minus. So we're trying to drive this ratio as close to 0 as we can. The D's are distances, which is a reminder they're always positive. So the D sub max here is a normalizing term. Why? Why do we want to evolve CTRNNs that minimize the distance between the palm and the object?
Because the classification is based on the sensation of feeling it. So if it's doesn't have its hand on the object, then what can it do?
Absolutely. Think about this CTRNN if you can. Think about 48 random tau values, 48 random biases, 48, however many weights there are. The vast majority of those, you can probably imagine what they do. This. There was probably, when they ran this experiment, very, very few CTRNNs that actually kept the palm or the hand in contact with the object, in which case, what is CS and CD going to look like? Where are they going to be relative to one another if the robot is not touching the object? The only sensors it has is touch sensors. It has proprioceptive sensors, which tell it its arm orientation in space. If it's not touching the object, what's the deal with CS and CD?
They're going to be almost entirely overlapped.
Of course. I'm blindfolded. You asked me to categorize objects, and I'm not touching the objects. I'm going to have a pretty hard time maximizing inter-category differences. So this F1 term here is a scaffolding term. And we're going to see a lot of scaffolding as we move forward in this course. As we start to evolve robots to do harder things, it's actually pretty hard to get started. So a common thing that good teachers and instructors and roboticists do is scaffold the learner's experience. That's what all of us teachers have been doing with you for the last 20 years since kindergarten, right? We didn't start with this in kindergarten. There's a reason. There's a scaffold. It takes a while to build up to certain concepts. That's true of abstract concepts and the real world in general, grappling with the real world in general, like active categorical perception. So formal education as a whole is an example of scaffolding. What are some other examples of scaffolding? There are tons. Think of all the difficult tasks you can perform. How did you get started on them? Or how did your instructor or your coach or your music teacher get you started? Let's go even further back. We're going to talk about locomotion in a moment, which is super easy. Look at me balancing on 2 points of contact. Super easy. What were your first scaffolding experiences when you were really, really, really young?
Like you crawl.
You crawl. You actually self-scaffold. Something that we and some other organisms are good at. Absolutely. You crawled for a while. And then maybe somebody came in and gave you some help, some scaffolding.
Then like maybe you take a couple steps and fall and then you keep going so you can.
So kids will grab onto things and hold on. If you watch little kids learning to walk, if you YouTube videos, they're pretty creative about scaffolding their own experience. It's very hard to get up and stay up if you haven't before. Parents will often grab grab a kid's hands, put the kid's feet on their feet, and then walk their kid through the experience. They're actually trying to generate the sensor motor experiences of walking. Okay, you're little, you achieve legged locomotion, and then there's this, one of your parents or your caregivers brings home this weird metal contraption and tells you to climb on it and start pedaling. The canonical example of scaffolding is training wheels. Yeah? They give the child the experience of what it means to pedal a bike, which they really don't have much of a precedent for, very unnatural. And then at some point, the caregiver, from their distal perspective, watching the child on the bike, make an estimate of competence. They can sort of judge when the training wheels are ready to come off. Okay, so F1 is a scaffolding term. It's going to evolve C-tier and ends that keep the palm in contact with the object as much as possible. And then F2 is going to reward the robot for active categorical perception. Specifically, it's going to reward for less and less, there's the minus sign, less and less of this thing, less and less overlap between C sub S and C sub D. Why are they dividing or normalizing this term by the minimum of the two areas? Why not just leave it as minimize the intersection between them? This one's a little trickier.
That incentivizes both CS and CD to be about as large as possible?
Not quite as large as possible, but it's taking away, by normalizing by the minimum of either, it's taking away the incentive that the evolutionary algorithm has to go in the opposite direction. If there is selection pressure during evolution, if evolution is trying to minimize this overlap, an easy way to minimize overlap between two boxes is make the boxes smaller and smaller. So without this denominator in there, and you got to try and run this in your head or try it in Pyrosim if you want, you get smaller. The evolutionary algorithm may start with boxes like this and then make them smaller and smaller, and now you get little overlap. The investigators didn't want this. They just wanted to minimize the overlap, but they didn't necessarily want to make small bounding boxes. Why are small bounding boxes problematic? What does it mean for a robot armed with neurons 47 and 48 that change very little when in the presence of an object?
Sensory experience every time.
Yes.
It comes in contact with
which is almost kind of a good thing, right? We're not just trying to magnify intercategory differences, we're also trying to minimize intra-category differences. If I'm manipulating a whole bunch of different ellipsoids, maybe I want to have sort of the same static experience. Seems good on the surface, but there's a problem underneath this. What happens if we have a C tier and N that does this? Perfect job. It's not overlapping the boxes. It's magnified intercategory differences. But now we come in with a different ellipsoid, and we don't place it like this. We don't place it like this. We place it halfway. We place it like this. We expose that C tier and N to an experience it's never had before. And this is C sub D. What do you think is going to happen?
It's not going to know. The tiny boxes have made it generalize really poorly.
It's going to this robot is likely to generalize very poorly. This is yet another thing that keeps AI researchers and roboticists up at night. You expose a trained machine to an unseen experience, and it doesn't generalize well. If the robot has a very, very small C sub D, it's got to hit a very, very small bullseye. You got to hope that that new ellipsoid manages to produce a trajectory inside here and not stray out and hopefully not into here. Kind of a subtle point. The reason I wanted to mention it is as we march forward into more complex and challenging behaviors, there are these subtleties that need to be dealt with. Okay, all right, so evolve, populations of C tier and N's against this fitness function, and at the end, they get back an evolved C tier and N in which there is absolutely no overlap between C sub S and C sub D. In the spirit of the minimal cognition experiments, they're going to now play the best evolved C tier and N back, the C tier and N with the highest fitness. They're going to play it back a whole bunch of times and try and understand how well it does, and does it generalize or not. Thankfully, these investigators went to the trouble of actually recording a video of how this works. So remember that we're going to expose this robot to some objects and start its arm and hand in position A, and then expose it to some other objects with a different set of initial conditions. We don't want the robot or the C tier and N to specialize to the starting position of the arm. Okay, here we go. Here's the most fit C tier and N operating the robot's arm when it starts in position A. Let's start with the actions that the robot is performing. Can you tell by looking at its actions whether it knows whether it's in the presence of a sphere or an ellipsoid? Let's see if I can put this on the loop here. How does the robot act when it's in the presence of spheres, and how does it act when it's in the presence of ellipsoids?
I think it acts the same regardless.
Looks the same to me. I can't see much of a difference. It's not doing anything very exotic here, right? No extreme motions, just, okay. How is it doing?
Pretty good.
How do you know it's doing pretty good?
You can see what its faceting it has in the bottom.
Exactly. Okay. So sphere and ellipsoid at the bottom. How did they figure out, the investigators, when they made this movie, how did they figure out how to draw the blue arrow? The blue arrow is representing the robot categorizing or failing to categorize. You'll notice it at the beginning of each of these evaluations, the blue arrow is pointing straight up. What does that mean? What's the robot telling us? It hasn't decided yet. Let's assume that this robot has this for C sub S and this for C sub D. What does it mean when the blue arrow is upright?
It's not really that enough.
It's out here somewhere, yeah. The time steps start to elapse in the simulation, and if the trajectory wanders into C sub D, the arrow drops to ellipsoid. If it wanders into C sub S, the arrow drops to sphere. What does red and green indicate?
Just the correct classification.
The correct classification, right? So you can see after a while, the robot decides.
You see in some of them, like the arrow will like flash to like the incorrect one before going.
Exactly.
Like in and out of the box.
Absolutely. This. Yeah. It's a sphere. No, wait a second. It's an ellipsoid, as we all do sometimes, right? It's, again, as always, this is not an optimal solution, but pretty good. And it kind of does it in a way that we might do it if we were given a very difficult, blind, active categorical perception task to solve. Yeah? Okay. Exact same C turn N, now running on the robot starting from a different initial position. The little green flashes that you see on the finger, those are the touch sensors firing on and off. What inter-category difference is it magnifying? The fact that the arrow's pointing straight up at the beginning means at the beginning, at least, in the first few time steps, spheres and ellipsoids feel the same to the robot, but then they start to feel different towards the end. How?
It looks kind of like it's rolling it one way and then rolling it the other, and it looks like it's doing worse because it's only basing it on rolling it back.
Okay. It's hard to tell, right? Yeah, it's kind of rolling it one axis and then another one. It's not an obvious extreme different action. There's some subtlety going on here, but from the robot's perspective, it feels different. So from our perspective, I'm going to turn the lights back on. From our perspective, the distal perspective, it looks tricky, right? Subtle. It doesn't look like it's doing a good job distinguishing between these objects. But from the robot's felt perceptions of this task, it can feel the difference. Okay. All right, so we've got some video to build up an intuition for what's actually going on. It does very well solving this task. Let's look inside the brain of the robot. In this case, they took the most fit C tier and N, and they replayed it in the robot 360 times. So 360 additional simulations. In 180 of those 360 evaluations, they took the ellipsoid and put it with an orientation of 0 degrees, 2 degrees, 4 degrees, 6 degrees, 8 degrees, 10 degrees, all the way around to 360. So they're rotating the ellipse underneath the robot's palm. And then up here, it's 180, quote unquote, rotations of the sphere. You rotate a sphere and it feels exactly the same to the robot. That's the scare quotes. Okay, and here are the 180 C sub Ds that got produced when in the presence, or sorry, not C sub Ds, these are the little bounding boxes. So inside each of these little bounding box is the little trajectory produced by 47 and 48 when in the presence of that rotated ellipsoid. Same for the spheres. How does the robot do? How does it generalize to these 360 additional quote-unquote objects? The big dashed box is C sub D. The big dashed gray box is C sub D. The big dashed black box is C sub E. How's the robot doing? How's it generalizing?
It looks like pretty well. There's only like 1 or 2 boxes that are outside the dashed line.
So there's a couple, here's 2 ellipsoids that the robot doesn't think is an ellipsoid. What does it think this ellipsoid is? A sphere. This one kind of feels like a sphere, but it's not quite a sphere. This one, robot says, I don't know. It's a sphere, an ellipsoid, I can't tell. But generally speaking, it does a good job. Okay. I mentioned that in this case here, in the case of these 180 spheres, the sphere is always placed in exactly the same place under the robot's palm, but not all 180 gray boxes are right on top of one another. I neglected to mention one detail, which is they put a little bit of noise on the robot's sensors when the robot is moving. Roboticists know that real machines in the real world never perform the exact same action twice. Man never enters the same river twice. We often approximate reality in simulation by sprinkling noise throughout the robot. It doesn't see perfectly, it doesn't act perfectly, and that noise has an influence on the values of 47 and 48, producing different boxes. Why are there two clumps of boxes in the case of the spheres? There's a detail of the experiment we did mention. The different arm positions, yeah? So sphere, it hasn't reduced intra-category differences perfectly. Same thing over here. Okay, this was the most fit CTRNN from one evolutionary run. They rewound the evolutionary tape. They started with a new population of random CTRNNs, evolved the robot against this fitness function again, and in this case, they got this result. Here's the sphere bounding boxes, and here's the ellipsoid bounding boxes, which are close, but there's still a little bit of a gap between them. So this is the best evolved controller, or the most fit controller from run number 2. Here's another one. Here's the second best evolved controller from run number 2, the second most fit one. And here's the third best controller from run number 2. It's got a very, very small C sub s. Not great, but still none of them are overlapping. They're close, but not quite. Okay. All right, we've spent a lot of time in this class talking about 2 neurons inside of one CTRNN inside of one robot. Let's go back to a question I asked at the beginning of this particular lecture, which is, why didn't they just look at the values of 47 and 48? And if the value of 47 was higher than the value of 48, that's the robot telling us it thinks it's in the presence of a sphere. If the value of 48 is greater than 47, that's the robot saying, I'm in contact with an ellipsoid. It would have been so much easier. Why did they go to all this trouble? They've got 2 objects they want to categorize. Why didn't they just throw in 2 additional neurons, 47 and 48, and be done with it? Why go to this effort? You take off on spring break and you're meeting one of your friends at an airport. You're looking around at a whole bunch of people, don't recognize them. Ah, there's friend X. Some part of your brain lights up saying, yes, I recognize friend X. Now you're waiting for friend Y, stranger. Ah, there's friend Y. Another part of your brain that's responsible for recognizing that particular person lights up. How many people can you recognize by sight? Maybe a few hundred, maybe a few thousand. Maybe there's a few hundred or few thousand parts of your brain dedicated to recognizing those people. From this lead up, you can guess that that's not actually how our brains do it. Why not? This was actually a hypothesis for a long time in neuroscience, that this is how your brain did it. It's known as the grandmother cell hypothesis. There's some cell or some neuron in your brain that lights up whenever you recognize your grandmother, and another neuron whenever you recognize someone else, and so on and so forth. That's not how our brains do things. What's the drawback of that solution? Seems pretty simple.
Well, it's not scalable.
It's not scalable, yeah? You've only got 10 to the 11 of those things in there. You want to make good use of your real estate. Okay, we've seen the robot categorize spheres and ellipsoids. Let's rerun the whole experiment, but now we're going to expose the robot to spheres, ellipsoids, and cubes. How do we modify the experiment? If we'd gone with the simpler approach, we'd have to add neuron 49 that's going to represent cubes. If we then added prisms, we've got to add a neuron 50. If we introduce dodecahedrons, we've got to introduce neuron 50. It's not scalable. We're starting to add more machinery to the neural network in order to allow it to categorize more and more objects. In this approach, if we added cubes, how would we modify the fitness function so that the robot can magnify category differences between spheres and ellipsoids, spheres and cubes, cubes and ellipsoids? Spheres, ellipsoids. Apologize for the sloppy terminology. Cubes. How does the fitness function change? How would we want these three bounding boxes arranged?
Taking up a lot of space but not overlapping at all.
We don't want any of them to overlap. So we could take the pairwise intersections, so the intersection of S and D, S and D, D and C, C and S, and we want to minimize all of those and normalize by the sizes of all three, and we end up, after evolution, hopefully, with something that looks like this. Makes sense? Here's C sub C, C sub S, C sub D. The robot will now probably feel all three of these objects differently. Okay, we could add a fourth one. We could add prisms and do the same thing. And we've altered the fitness function, but we haven't increased the size of the brain of the robot. Generally speaking, that's a good thing to do. We want, in robotics, generally speaking, to pack more cognition or more capability into the robot without making the brain bigger and bigger and bigger. Mother Nature probably was trying to do the same thing with the hominid line leading to us, because making human brains bigger and bigger and bigger is very problematic for the mother. Not a good thing to do. Yeah? A very difficult optimization problem to be solved here. Okay, last thing, and then we'll move on to legged locomotion. If we ask somebody, if we showed them a sphere, an ellipsoid, and a cube, and we asked them which one doesn't belong, what would most humans say? Regardless of mother tongue, regardless of nationality, culture, religion, generally speaking, for humans, which one doesn't belong? This is not a hard question. Cubes, obviously, right? They're more different than spheres and ellipsoids. If you were to ask us, we'd say, well, because geometrically they're similar, right? Thinking about thinking is misleading. Put someone in the brain scanner, scan their motor strip, and their palms will light up. Most people, if you ask them which one doesn't belong, they're mentally manipulating those objects, and they can feel the edge of the cube digging into their palm, but not so much the sphere and the ellipsoid. If we wanted to try and align the robot's experience with ours, we want the robot to feel these three objects differently, how would it? In the three bounding boxes I just had drawn on the board, they were more or less equidistant from each other. The robot would have answered that question incorrectly. It would have said, well, all three classes of objects feel different, and none of them is more different than the other. How would we modify the fitness function to try and align the robot's felt perceptions with ours? How do we want to arrange CS, CD, and CC now? We want to make the cube feel more different for the robot, than the sphere and ellipsoids feel, like for us, what would we do?
We just want to maximize the distance between the cube bounding box and the other two.
Something like this, right? We might now put in some terms to the fitness function that try and maximize the distance between these. This is known as the alignment problem in robotics and AI. Solvable for concrete things like spheres, ellipsoids, and cubes, but harder when you get into more abstract categories like child, parent, young, old, important to me, less important to me, and so on. Okay. Any questions about that before we switch gears? Okay. All right. Legged locomotion. I'll start with the question. I might have asked this question already. Why don't plants have brains?
Because they don't move.
They don't move, right? Okay. There is a marine animal known as the sea squirt. In its juvenile stage, it swims happily through the ocean, filtering out plankton and eating. And then as it transitions from the juvenile to the adult stage, it finds some big rock, clamps onto it, and holds and makes a bond to that rock for the rest of its life. The first order of business is to clamp onto the rock. Second order of business, it liquefies and digests its own brain. It no longer is ever going to need to locomote in its lifetime. Brains are huge energy hogs, great source of food, away you go. Sea squirts are often equated with professors immediately before and immediately after getting tenure. Okay, sorry, an old academic joke for you. Okay, all right. All of the stuff going on in here, there's a lot going on in here. All of it is rooted in locomotion. You're all heading off on spring recess. You're going to take trains, planes. You're going to walk, bicycles. You're going to swim. You're going to go scuba diving. You are about to go through a lot of problem solving. Many of you, I'm sorry to say, your flight's going to be canceled, and you're going to have to figure out another way to get from point A to point B. You are about to enter into a complex admixture of cognition and locomotion, getting from point A to point B. They are very intimately connected. Generally speaking, in AI and robotics, that connection is overlooked. How much effort does ChatGPT put into getting from point A to point B? Nada. Yeah? Okay. So let's talk about locomotion a little bit and see how that starts to create evolutionary selection pressures favoring cognition. How exactly is cognition built on the scaffold of locomotion? Okay, here we go. Okay, I forgot to bring in my copy of this book down here, one of my favorite books. If you're enjoying this course, I highly recommend this book, Principles of Animal Locomotion, written by Alexander. I've just copied and pasted the table of contents from this book. I love this book for many reasons. Basically, he tours through all of the many ways that Mother Nature has discovered to get organisms from point A to point B. Alexander starts off by talking about the one and only one organ, or usually the only organ or type of tissue that is used by organisms or animals to get from point A to point B. Every organism that does move around ultimately is usually doing it through motors. Plants, or at least their seeds, move around, but it's passive. Yeah? Okay. He goes through the energy requirements of locomotion, size differences, and as he starts to pave the way towards animal locomotion, he points out very quickly that in solving this problem, any organism that has to solve the problem of locomotion, that organism has to strike a balance between at least 4 antagonistic desiderata. Desiderata meaning you want these things. You want all four of these things. If you don't have them, you're in trouble. But they're antagonistic desiderata, meaning as you evolve or learn to get better at one of them, you usually have to pay a cost in terms of one or more of the other three. Yeah? Different species strike different trade-offs between these four things. Some species are really good at one of these. For example, displacement. You can think of displacement as velocity. We are not the fastest creatures on the planet. What is? Let's restrict our discussion for the moment to land locomotion. Locomotion over land. Who's the fastest? The cheetah. Yeah, okay. Very, very fast. What does the cheetah give up in order to be the fastest? Robustness, yeah, okay. So, yeah, cheetahs aren't very fast on ice. There's a very specific niche in which they're very good at going very fast. They're big cats. They're pretty adaptable. They do take a little bit of a hit in terms of robustness. That's not the one where they really paid up. What did cheetah eat? And eat a lot of.
The carnivores, they need a lot of energy to move that quickly.
Absolutely, right? I invite you to go out today and try and reach your top speed or the top speed of a cheetah. You're going to get pretty hungry pretty fast, yeah? Huge energy requirements. Moving at that speed is usually something only a predator would entertain. Of course, the prey also have to try and go pretty fast, but the prey tend not to maintain whatever top speed they do for very long because it's harder for them to recover it from plant material. Take your favorite land animal or marine animal if you like, and think about how fast does it go, how slowly does it go, how robust is it, how many different environments can that animal move through, what are its energetic requirements, and how stable is it? Okay, let's take our favorite species, us. What are we good at? We're fast, but not that fast. We're robust. We can move through lots of different environments. Now, thanks to technology like clothes and stuff like that, we're not actually that robust. A naked human isn't going to do very well in a lot of biota on Earth. We're okay, but not that great. But we're really, really, really good at one of these four things. You are really good at one of these four things.
Stability.
We're not very stable. How many of you have fallen on the ice this winter? We're not that great.
Energy.
Yeah, there's only a few left, right? Okay. At walking speed, if you're in good shape, you can travel, I forget how many miles it is on like half a Big Mac. We are very, very good. There's an interesting hypothesis about early hominids like us. We hunted prey by just getting a bunch of our friends together and just walking in a straight line for a really long period of time. And prey out on the African savanna would run away from us, but your friends are spreading out and starting to walk in a closing circle. And eventually, if it's a very warm day, prey will just overheat or run out of energy. And as long as you as a hominid are walking at a steady enough pace and you've got some water with you, you can hunt down very large game just by walking them to death. Whether that's true or not, who knows? Interesting hypothesis. This is the thing that we are very good at. Turns out we did it by assuming the bipedal stance. We gave up two of our appendages for locomotion, and with some other physiological changes, we mastered bipedal locomotion, which, oh my goodness, suddenly freed up these forelimbs for other things. There we go. We already have a connection between modes of locomotion and striking a different evolutionary balance between these four antagonistic desiderata, and suddenly creating possibly evolutionary pressure for using these things for other things, like active categorical perception. Okay.
Alexander's book continues. He starts with locomotion on land using some of the very earliest modes of locomotion, like peristalsis. When we get to soft robotics, we're going to see a lot of robots that actually do crawl and push their way through narrow apertures in the earth. It's a very, very old way of moving. If you're tubular and soft, you expand the volume of one part of your body, which increases your friction with the ground or the walls of the tunnel that you're traveling through. You contract the back part of your body, which contracts forward. Then you relax the front part of your body, expand the middle part, and you have this traveling wave of peristaltic motion traveling from the front of your body to the back of your body, and that ends up displacing your whole body forward. Repeat, repeat, repeat. Animals that crawled up out of the sea onto land, they literally crawled using peristalsis, most of them. Mother Nature tends to recycle and reuse inventions from a long time ago. You also still perform peristalsis. Not peristalsis for locomotion. We've moved far beyond that. But there are parts of your body that do peristalt. What are they?
Digestive tract?
Your digestive tract. Food and air and drink that comes in is literally pushed down through the body using peristaltic motion. Okay. Alexander moves into more familiar territory like walking, running, and hopping, things that we're pretty good at. Climbing and jumping, again, we're pretty good at. If you've never watched a video of a gibbon on YouTube, I highly recommend it. They're fantastic at brachiation. I showed you a robot that brachiates a few weeks ago. Homo sapiens sapiens, we're kind of good at brachiation, but it takes a lot of practice and it's exhausting for us. Crawling and burrowing. Gliding and soaring, hovering, they're animals that hover, powered forward flight, pterodactyls, insects, birds, moving on the surface of water, swimming with oars and hydrofoils, swimming by undulation, and finally, swimming by jet propulsion. Who swims by jet propulsion? Squid, cephalopods, octopi, cuttlefish. Yeah. When you stop to think about it, it's amazing the diversity of ways that organisms get from point A to point B. Okay. As we've just mentioned, all of these diverse strategies, they're different ways of moving, but underneath the actual mode of transport, the organism is striking a balance between these four desiderata. Yeah? Okay. Let's apply this intuition of these four desiderata. Snake-like or reptilian locomotion is actually very good on land. Snakes and lizards move pretty darn fast. They're pretty energy efficient when they do so, kind of. They're stable. It's hard to fall over if you're already lying on the ground. Why? Why did mammals ever evolve away from reptilian lineages, where mammals tend to have their legs vertically underneath them rather than lying flat on the ground? What's the drawback of snake-like or reptilian locomotion from the perspective of these four? Some of you are traveling to southern climes next week. You're going to see lizards on the walls and the ceilings. They're pretty darn robust. Now, reptiles, for other reasons, can't invade cold climates very well, but it's not because of their locomotion capabilities. They can move over way more surfaces unaided than we can. It's definitely not robustness. Reptilian locomotion, where you're dragging your body along the ground, it's a pretty robust way to do things. They're very stable, they're very robust.
Energy.
So we've only got a few left, right? If you're dragging your belly along the ground and you've got to lift your arms horizontally, this is a lot of effort. There's a lot of friction, especially when you're in warm climates where heat is an issue and heat dissipation. Not very energetically efficient. Best to be as vertical as you can and keep as much of your body off the ground. So we, Homo sapiens sapiens, we're at almost the opposite end of the spectrum. We are extremely energy efficient. I've mentioned this, I think, before. When you think about bipedal locomotion, and we're going to talk about bipedal locomotion specifically when we get back from break, as you're walking, the moment your stance foot, the foot that's you're standing on or is in contact with the ground, the moment your stance foot leaves the ground and becomes the swing foot, all of the muscles in your leg go slack, and your leg is actually resting and getting rid of carbon dioxide and pulling in oxygen while it's swinging, and then goes back to work the moment your heel strikes the ground. You're all going to leave this class with a weird look on your face because you're going to be feeling that fact. Most of the time you're not aware of it, but you can actually feel your legs relaxing. Very, very energy efficient. Okay. Okay. So let's have a look at this trade-off in a little more detail. The other thing that's super fun about Alexander's book is he describes a whole bunch of crazy experiments that have been done with animals, and almost all of them did no harm to the animal, to try and understand exactly what this trade-off between these four desiderata looks like. So some familiar experiments here. You put an animal or a human on a treadmill, you put a mask on, and with that mask, you can measure oxygen and carbon dioxide exchange. The more oxygen that's going in and the more carbon dioxide that's going out, the animal or the human is burning more calories. Yeah? So you can measure energy just by looking at the exchange of gases while someone or something is on the treadmill. Okay, so let's start with this plot down here. On the horizontal axis here, this is for humans. For the horizontal axis down here, we have speed in meters per second on the horizontal axis. So they put, in this case, men on a treadmill, put a mask on, and slowly turned up the speed of the treadmill. And they measured the amount of energy that were being expended by those men on the treadmill. What's happening? Not surprisingly, the faster you turn up the treadmill, the more they're huffing and puffing. But this relationship is more complicated than that. What's happening?
At a certain speed, running becomes more efficient.
Because what's happening? Why is it becoming more efficient? Walking is very efficient here, but if you try and, again, you can try this at home, be careful. You can turn up the speed of your treadmill and try and continue walking. It gets very uncomfortable and super exhausting very, very, very quickly. And then when you switch to running, at least for intermediate speeds, it becomes a little bit more comfortable again. Why?
Part of walking is using your heel to control your speed as you go forward.
Okay.
Makes it a lot less energy efficient if you're trying to conserve momentum.
Absolutely. So you have to start pushing with your heel harder and harder. Remember, one of the most comfortable things about walking, and possibly what made us the apex predator in the African savanna, is walking. The advantage of walking is energy efficiency, but in order to get that energy efficiency, the leg has to be a pendulum for half the time. As your walking speed speeds up, your leg, no matter how long it is, has a natural frequency that it likes to swing at. If you want it to swing forward at a faster speed, at some point you have to give that up. You're now strictly no longer walking, you're actively moving your swing leg, not a comfortable thing to do. So at some point it gets exponentially inefficient and most of us switch. So it turns out in humans, there is this switch, the speed for most of it. We have slightly different speeds depending on who you are, where it feels good to switch from one mode of moving to another. We just finished a lecture in which we talked about active categorical perception, in which there are no categories out there in the world, but when we interact with the world, suddenly these categories pop into being. Here it is happening again in terms of, in this case, the whole human body. The treadmill itself is increasing velocity at a constant rate. There's no categories of speeds for the treadmill, but for the person on the treadmill, there is. It has to do with us. Okay. Here's another interesting experiment here. So in B, they set the treadmill to 1.5 meters per second, and they commanded the people on the treadmill to walk with higher frequency or slower frequency, and they measured the total power output. What's happening in this case? Another detail of the relationship between displacement, physiology, and speed. Yep.
I'm guessing it, because like the little valley there is
Yep.
when, like you mentioned, the leg swing becomes effortless.
This is, let's talk about this valley here. So horizontally, it's at about 1 hertz. So 1 beat per second or 1 step per second. At that particular frequency, for most adult males, that's the beat frequency or the walking frequency at which we burn the fewest calories, which is exactly what you said. For a 6 foot tall male, 1 hertz is about the speed at which you can relax all the muscles in your leg, and your leg will swing back and forth at about 1 swing per second. Slightly lower for most females and children, longer for basketball stars and so on. Yeah? Okay. So there is something about 1 hertz that feels good for most humans most of the time, or at least for our ancestors, because most of the time our ancestors were walking. For us, we sit most of the time. But generally speaking, there was a natural frequency that felt good for us. Turns out that if you put humans in a brain scanner, your brain emits patterns at a whole bunch of different frequencies. The strongest frequency that your brain emits patterns at when you're lying still in a brain scan is 1 second. Unexplained why that's the case in brains, but pretty strong circumstantial evidence that there's some relationship between our ancestors' most common activity and the speed at which the brain tends to operate, or at least one of the speeds that the brain operates at. Another connection, possibly, between locomotion and cognition. Okay, so we just introduced this concept of gaits, which of course you're all intimately familiar with. Different animals have different numbers of gaits, so we'll introduce a little bit more terminology to arm us for this discussion. I already talked a little bit about stance leg and flight leg. There is also stance phase. For a legged animal, stance phase is there's at least 1 foot on the ground. Flight phase, no feet on the ground. It turns out that for horses, are there any horse people here? I'm probably going to get this wrong. I'll try this. Okay, here we go. In trotting, there is a very, very short fraction of time during the gait cycle in which there is a flight phase. There it is. If you ever watch a horse trotting, it's very, very hard to actually see it because the feet don't come off the ground very far, and it's for a very brief moment in time. Over 100 years now, a professor at MIT wanted to actually solve this question. Were horses flying? Were they off the ground for a period of time during trotting? Over 100 years ago, photography wasn't very good, but he came up with this method of taking a bunch of pictures very quickly, at a 1/10 of a second, one after the other. He managed to pull this off and then put them together and flip back and forth from one to the next, and something amazing happened. He could see the horse moving without actually looking at a horse. It was the very first movie that was ever made. It was made to answer this question. Okay, it's got nothing to do with robotics, just kind of an interesting anecdote, I think. Okay, as we move up through the gaits of a horse, there is more and more of a flight phase. Why for horses and why for us does it feel comfortable to run at high speeds? It feels comfortable because you're still burning a lot of energy at a high speed, but you're burning less than, in our case, if we walked or if the horse trotted at a high speed or cantered or whatever else there is. What is it about running that's energy efficient at high speeds? What happens during the flight phase in galloping for horses or running for us?
There's no friction.
There's no friction. You're not in contact with the ground. None of you is in contact with the ground for a period of time. So what can you do while nothing is in contact with the ground? What should you do while nothing is in contact with the ground? You can relax. For a little while, don't relax too long, but you can take a short breather during the flight phase. Okay, all right. You've all seen these sorts of things before. All of the different organisms or different species are striking different balances between energy, stability, displacement, and robustness. Individual species, like dogs, are also slightly switching these trade-offs at different speeds. Okay. A little bit more terminology to arm us for the next few lectures: static stability and dynamic stability. So I mentioned stability is one of these four desiderata. There's different kinds of stability. There's static stability. Static stability means as you're moving around, if for some reason you need to stop displacing, if you need to stop moving, you don't fall over. Someone or something that is statically stable, at any point as it's moving, it can freeze and not fall over. Dynamic stability is a little trickier. Dynamic stability is dynamic meaning change. So as you're moving, if something perturbs you from outside, somebody pushes you or you happen to touch some ice, you're able to slightly change your dynamics. You're able to slightly change how you move and recover and keep moving. That's dynamic stability. Okay. As you're walking, and by walking we mean having at least 1 foot in contact with the ground at all times, are you always statically stable while you're walking? How do we answer this question? You need to think about how your body is oriented in space during the gait cycle, from one step to the next. And at every instant of time during that process, during that cycle, could you stop and not fall over? You've all been walking for decades. You've got plenty of personal experience. Pretty much, right? Almost. There are brief instances of time in which you can't, and you don't notice it because at that moment you shift your weight towards the forward foot and you're statically stable again. Okay, most of us, once you're good at running, you're also relatively dynamically stable. When you're late for class and you're running across the ice and something bad happens, maybe not, but most of the time we're dynamically stable. How do we determine, aside from doing this kind of anecdotally and from felt experience, how do we do this more rigorously? Well, we can consider our own or an organism's or a robot's polygon of support. At every moment in time, we can basically count the feet that are in contact with the ground and determine where exactly they are. So let's do this for horses. We've got left front foot, left back foot, right back foot. And for one of these gaits, at a given moment in time, let's assume that the horse's left front, left back, and right back foot are in contact with the ground. We draw a polygon around those points of support, and in this example, we get a triangle. We then compute at this moment in time the center of mass of the organism. Where is it? We then take the horizontal component of the center of mass. So if this is more or less where my center of mass is, we drop it back down onto the ground. And if that center of mass falls within my polygon of support, I'm statically stable. If you balance on one leg, you stay balanced as long as your center of mass is within your foot. If you now go back and think about yourself walking, there's a period in time in which your center of mass is balanced over your back foot. You're statically stable. As you lean forward, but before your front foot comes in contact with the ground, there's a moment at which your center of mass passes outside your back foot. And for that brief moment of time during walking, you are not statically stable. If you try and stop, you're going to rock forward and hopefully catch your balance. Okay, we've got 5 minutes left. You're statically unstable if, as I just mentioned, there's a period of time in which your center of mass is outside your polygon of support. Okay, let's go back and look at some energy versus speed again. In this case, we're going to work with ponies. In this case, they were working with 100-kilogram ponies, and the investigators observed ponies walking or trotting or galloping when moving freely in their paddock. So they're just out there doing their thing, and they naturally switch between these gaits. And they were observed to be traveling at these 3 gaits of their own free will at these various speeds. They took those ponies and then put them on very big treadmills and gradually turned up the speed of the treadmill, and surprise, surprise, they saw the ponies switching from walking to trotting to galloping. And this is how much energy the ponies were burning while on the treadmill. What's the relationship between the curves and the black bars at the bottom? What does that relationship tell us?
They're moving in the most energy optimized way.
What a surprise, right? They tend to be moving at the speed that's most comfortable. They're moving most of the time at their energy minimum for the speed that they want to be moving in at that moment in time. Okay. I always pause here for a moment to show our good friend the octopus. Every rule that we're going to talk about related to legged locomotion is broken by this animal. Pretty much every rule that applies to higher animals, the octopus always seems to be the exception. Here's land-legged locomotion. What gait is this? Who knows? Okay. Maybe a good place to pause before we start talking about walking robots. You have a quiz due tonight. You're working your way through the assignments. Have a great spring recess. We'll see you in a little over a week's time.